Alright, in this video we're going to be talking about relations. Now, relations you've actually been using for a long time without actually knowing that that's what it was called when you were using it. Basically, a relation is just a set of ordered pairs. Set of ordered pairs. Ordered pairs. And, oops, that's an R, pairs. Okay, an ordered pair is just essentially similar to a coordinate. We've got an x coordinate and a y coordinate. And they're called ordered because the x coordinate comes first and the y coordinate comes second. There's a strict order to them. Okay, so a relation is a set of ordered pairs. So let's create a relation. Let's create this relation, this set S. It's a relation of ordered pairs. Make it contain 1, 2, and 2, 3, and 5, 6, and 7, 8. Okay, so it's a set. Yes, it's got braces and a big letter to name it, and it's a set of ordered pairs because there are 4 elements and each one is an ordered pair. Okay, so that's basically all it is. But you can write ordered pairs as sort of a rule, if you like. So for this particular case, we could write this ordered pair in the following way. We could write this relation S as being the set of ordered pairs x, y such that, so these two dots are like writing such that that y equals x plus 1. So you notice in this case the y value is always 1 higher than the x value in this particular case. So my rule is y equals x plus 1. But that's not all, because x has to be within the set, so the first value has to be within the set 1, 2, 5, and 7, because those are the only x values. We don't just have unlimited numbers of these ordered pairs, we've only got 4 of them, so you have to say what x is. And then we've got to close our braces off to close it up. So there you go, there's 2 ways to write this down. And once you've got it, you can also plot it fairly easily if that's what you want to do. Whoops. Let's get rid of that. Oh man. So here we go. We can plot this ordered pair if we like. This relation, sorry, with 1, 2. So here somewhere. And 2, 3, 2, 3. And 5, 6. And 7, 8. And I should really be labeling all of these. 1, 2, 2, 3. So there we go. We can label them like that. Why do we bother with this whole big thing? That's just to be really, really clear about whether or not we're doing a discrete graph or a continuous one. Now, a discrete one basically means there's specific points and you can count those points. So here we've got 4 very specific points. So it's discrete. That's discrete, that case there. Now what we're going to do is a continuous case. So a continuous case would be this second set T, and we've got to define our rule. So it's the set of ordered pairs x, y, such that y equals x plus 1. So it's the same rule, but then if I say that x is any value within the real numbers, so R for the real numbers. Now remember, the real numbers, it includes basically everything. It includes the integers, so integers including negative numbers and positive numbers. It also includes rational numbers, so that means like fractions, which have an integer divided by an integer, so it could be negative 217 divided by 6. That's a rational number because it's got an integer divided by another integer. And it also includes irrational numbers like the square root of 2 and pi. So the real numbers includes everything. So if I was going to plot that on a set of axes, it would look more like that. It would be a continuous line. And you would not be able to find, you'd not be able to count the points on this line because there's, because you can't sort of see them, if you like. They're not discrete or countable. So that's a continuous case there, and you can see visually how it's different to a discrete case. So there we go. There's one other example perhaps that would be useful to mention. So let's define another one. So I'll create another relation. I'll call it V. Oops. Set of ordered pairs x, y, such that x squared plus y squared equals 1. And I'll say that here x can be anything in the real numbers again. Now, it might be interesting just to plug this into a calculator if you want to. Otherwise, you may remember, maybe I won't explain it for now, but what this looks like if you plot it is actually a circle with the radius of 1. So in other words, this is a unit circle. Oops. Unit circle with a radius 1. So it's got a unit radius, so it's called the unit circle. It's a very important thing that we're going to be discussing lots more later in the course. I just wanted to show you this relation because this relation it's allowed, if you like. So next we're going to talk about functions, and I'm going to show you why this relation is a relation, but it is not a function. So get excited for that. Alright, well, maybe I'll stop it there. No, actually I won't stop it there. There's one last thing, which is to say that in cases like this one here, where it says that x is within R, so in other words, that's the domain that we're talking about, which we've mentioned already. Domain, it's the possible x value, so here's that domain, here's this domain. So two different domains. When the domain is a set of real numbers, that's sort of like the default domain, if you like. So often, if this default domain is indeed the case, we don't bother writing out this whole big sort of professional or specific way of writing our relation. We just write the rule. So in the case when our domain is the real numbers, we might be more inclined just to write y equals x plus 1. And that is sort of what you've been in the habit of doing in your years 7 to 10 so far. So just thought I'd flag that for you. Okay, we're done now. See you later.